see much. That's good enough. Okay. This is just, there's not even anything about an acceleration formula on here. This is just making sure you get the gist of acceleration, that you've got a conceptual understanding of it, and that's really what this class is supposed to be about. So, yeah, except it's called Physics 100 now. I'm supposed to change, everywhere it said conceptual physics on things, I'll change it to Physics 100.
Yeah, numbers.
But for conceptual, there is a lot of math. Looking at the first test that they gave you, that I'm supposed to give you the common assessment, there are quite a few problems on there. So we've got to deal with that, even though this is all supposed to be conceptual. These first two sentences here, they look exactly the same, except this one says position and this one says velocity. So blank tells you how much something's position changes during a second. Blank tells you how much something's velocity changes during a second. What goes in the first one? How much your position changes every second is what? It's your speed or your velocity. And so velocity is where you are is changing by so many meters every second you're moving. And that's what velocity tells us. This other thing tells us how much your speed is changing. So whether you're getting faster or slower, and that's acceleration. Acceleration can be positive or negative. When acceleration is positive, if I say you've got a plus 6 meter per second acceleration, what does that mean? Getting faster, speeding up, say it however you want to. And acceleration is negative when something's slowing down. The tricky thing, if you hear acceleration, you have to be wary, because that might have a positive sign in front of it or a negative sign. Just because I say, what is something's acceleration, don't assume that I mean how fast is it speeding up, because I may be wanting you to tell me that it's got a negative 5 meter per second squared acceleration. So that's kind of tricky. But there's also a term for negative acceleration.
Deceleration.
Deceleration. And when you hear that, that is unambiguous. That means there's something is slowing down. You don't have to wonder whether I mean positive deceleration or negative deceleration. That doesn't make sense. The common metric units, this is what you'll see most of the time, and by the end of the year, I expect that's all we're ever going to use. Meters per second squared. I have a little bit of a problem with meters per second squared when introducing this subject, and here's the problem.
Exponents come before division.
Well, no, just this. Picture a square meter or a square foot. Can you imagine that? You just look at the floor. These squares are square feet. But now picture a square second. Doesn't make sense. So it's just kind of a bizarre thing. What exactly that means, you can't wrap your mind around that. Those are units. There's a reason those are the units. It's easy to write. That's why we write it. But a better way in the beginning, in my opinion, is to write it like this. Start out with meters per second. That's velocity. And this little slash, that's the per part. So this is how many meters you're going in every second. And then add another per second to that. So first you've got the velocity part. And the velocity is telling you how much your position in meters is changing every second. But if you take that whole velocity thing, lump it together, and put another per second with it, now we've got how much is this velocity changing every second. So meters per second per second. A lot of the world doesn't really talk in meters per second. They talk in feet per second per second. When you jump off a building, every second you're going 32 feet per second faster than you used to. So that's feet per second per second. And after 2 seconds, you're going 64 feet per second.
Wait, the world talks about that?
That's the thing I heard most before I got into physics. Before I ever took a physics class,
really?
And I talked to people about how fast would you be going if you jumped off whatever, they would always tell me 32 feet per second. That's how fast you'll fall. But
yeah, I just thought feet were only
yeah, feet it's antiquated, and we don't use it much in physics.
Okay.
So Now, the author of the textbook, he likes to do this kind of thing, which we already have been over. He likes to use kilometers per hour dot second. And that's just another way of writing kilometers per hour, which isn't so bad. I mean, that's on your car speedometer, so it's not all that weird, per second. So that's the velocity part.
So we're dividing and multiplying.
You're dividing. All those slashes are division symbols. So it's kilometers divided by hours and the whole thing divided by seconds. Gets a little bit confusing. When you divide this by seconds, another way to write it is kilometers over hours times seconds. I just want you to know, when you see this, what he's saying is that every second you adjust your velocity by so many kilometers per hour. You can also, he might even do it like this. He might even write it miles per hour second. So that would be, this is the velocity part. This is how many miles per hour you're going every second. So if you're doing 3 miles per hour per second, that means in your car you're going 50. 3 seconds later, or sorry, a second later you're going 53. A second later you're going 56. That's what that means. This next question, this is really the most important question on the page. The quiz had the question, if I say someone has a velocity of 4 meters per second, what do I mean? And the answer to that was every second they move 4 meters. This is the analogous question with acceleration. A runner has an acceleration of 6 meters per second squared. What does that mean? And don't just say it means they have 6 meters per second. Don't just write that out. What is it? Everybody explain what it deep down really means.
That every second the runner increased his velocity by 6 meters per second.
Yeah, you could say it that way. You could say every second the runner increases his or her velocity by 6 meters per second. That's one way to say it. I'm going to say it kind of like I did with velocity notes. I'll say for every second that goes by, 6 meters per second is added to his or her, to be fair, velocity. So that's what it means. It's just how much do you add or how much do you subtract. When you have a plus, you add it. When you have a minus, you subtract it. And it's really simple, but when I ask several people this, I get a lot of answers like, it's the number of meters you add every second. It's not, acceleration isn't about adding meters, it's about adding velocity or subtracting velocity. Adding meters, subtracting meters, that's velocity. That's adding distance to where you are. Okay, now just some simple examples. Fred is walking with a velocity of 1 meter per second. He speeds up. After 1 more second, he's going 3 meters per second. What's his acceleration? Blurt it out if you know.
2 meters per second.
2 meters per second per second. I can write it like this. I don't mind if you write it that way. Or you can write 2 meters per second squared because it's just faster. If you're okay with the whole idea of square seconds. And this is just telling us that's how much he's adding on for every second. If he kept going, he'd be adding another 2 meters per second in the next second. Now Wilma's riding a bike. She's got a speed of 12 meters per second. Her acceleration is negative 5 meters per second squared. How fast is she going to be going after 1 more second? 7. So this is what you do to the current velocity. You subtract that much every second. So she'll be going 7 meters per second. How about after 2 seconds? She'll be going 2 meters per second. How about after another second?
She'll be riding backwards.
She'll be riding backwards at 3 meters per second. She'll be going negative 3 meters per second. That'd be pretty cool if she could do that. Some people can. Anybody ride backward on the bike in here? I can only ride backward if I sit backward. I can't actually pedal forward and then pedal backward. I can sit on the handlebars and ride backward.
Huh.
Can I flip this?
Oh, there's a backside.
Oh, now, at this point, don't look at your paper. I'm going to be covering up certain parts of it and asking you questions about things. So I know it's real tempting because it's sitting right there in front of you, but try not to look at it. Well, we'll write something on it in a second. All of these graphs, the left one, middle one, and right one, they all go together. They all represent the same event. So this is showing an event. This is showing the same event. And this is the kind of graph that you have made in the past. That's the one where you stood in front of the motion sensor and you walked toward or away. So if I've got a motion sensor here and I want to make that graph, do I walk toward it or away from it?
Away.
Away. So my distance to the sensor should be growing as time goes by. So I walk away. How do I walk away? Slowly and increasing my speed. So this is acceleration here. And it's constant acceleration. This doesn't really look very constant because it's curved, but that's what constant acceleration looks like on a distance and time graph. Here's the velocity graph that goes with it. Again, they're exactly the same event is being pictured on both of these. Now we can see with some detail. So look at what's happening to the velocity every second. Here's 0 seconds, 1, 2, 3, 4, 5. Look at how the velocity is changing. Think to yourself, don't blurt it out yet. Think about what the acceleration would be and how you would write it out, what the units would be. I'm going to pick somebody and see if you can get it. You're supposed to figure out the acceleration. Mike, I'm going to pick you if you don't think about this. So you're looking, Mike, look up there where I'm pointing. See if you can look at that and figure out what the acceleration is. Don't look at your paper. Willie, do you have any idea what the acceleration would be?
10 meters second squared.
10 meters per second squared, yeah. After 1 second, you're going 10. After 2 seconds, you're going 20. After 3 seconds, 30. So 10 is being added on to velocity every second, so that's the acceleration. To the right of this, over there on the paper, I can't really point. Over there on the paper, there's a graph, don't look at it, of acceleration versus time. So instead of velocity up here, there's acceleration. What do you think that graph is going to look like? Straight line going where? Angling up, angling down, flat?
Flat.
Flat.
Acceleration of change.
Flat, and it should be right on 10. So that's the acceleration. This is constant acceleration. It's 10 the whole time, and that's what happens to your velocity when you have constant acceleration. If this were a car and this was your acceleration and suddenly somebody hit the gas or pushed the gas even farther, this would jump up and then this would start to curve up. But somebody's just accelerating constantly here. Now going back to this one, the point of me doing this right now is just to get a feel for how all these things fit together. So I'm not going to give you a bunch of questions about these yet. But looking at this, you know from experience that this is what the graphs look like when you walk away from the sensor faster and faster. But why? Why is it curved when something's accelerating? On this graph of distance versus time, why does it curve upward? Think about that for a second. And again, I'm going to pick somebody. If you don't know, just say you don't know and I'll pick somebody else. Again, the question is, why does it curve upward? Instead of just maybe going upward. Let's see. Taylor.
Not really sure.
That's okay.
Just because you're going faster and it's like not.
You're going faster, but why does going faster make this graph of distance? There's nothing, speed isn't on here, it's just distance. So why does it create this curve on the distance graph?
Because you're going further away? Like, is it,
You're going further away, but you could be doing it like this. It could be in a straight line and you'd still be getting farther away. You haven't said anything wrong so far, it's okay. Let's see, let me pick somebody different. Cheyenne.
Well, you're increasing the constant amounts.
You're increasing the speed.
Yeah.
That's true. But again, what we're seeing is this curve here. And I mean that sort of explains it, but sort of not. Marissa? Speak up a little bit.
It wasn't at the constant.
I can't hear you. I heard it wasn't at the constant.
It's not at a constant because it was a straight line.
All true, but there's something more basic that can be said about this graph to say, here's how you can tell that this was acceleration, or here's why acceleration makes the graph look like that. Josh.
Because like for each second, your distance gets farther than the last one, and then for the next second, the distance you're traveling in that second gets farther.
So for each little time interval, like from 0 to 1 seconds, how far you go compared to 1 to 2 seconds compared to 2 to 3. As time goes by, over a 1 second interval, you're going farther. Is that what you're saying? Yeah. That's, and nobody said anything wrong. That's just probably, I think, the best way to illustrate it. If you look at the first second, when somebody started out here, at a time of 1 second, this is 50, this is 0, so maybe they had gone 5, 6 meters. Now, if I'm going to try to move up to an easier time. Okay, I'll just go to the 4 to 5 second interval. This is a 1 second interval. Right here at 4 seconds, they've gone about 75 meters. At 5 seconds, they've gone about 125 meters. So they're going about 50 meters in that 1 second. And then if you go to the last second interval, at 9 seconds, they're at the 400 meter mark. At 10 seconds, they're at the 500 meter mark. So now they're going 100 meters in a second. So the reason this is curving is because it's showing down here very little upward movement over time, very little distance covered over time. And as you cover more distance in the amount of time, this is going to slope upward, slope upward, slope upward, until, you know, if it kept going, it would get even steeper, and you'd have really big distances for every second. Don't look at your paper yet. I'm going to go to the second one. Let me think about what I want to expose on here. Okay, same thing as last time, I think. Except it's kind of cheeky. So these two graphs, what are they showing? Just blurt it out. Deceleration. And think about it, but don't say it yet. See if you can calculate in your mind what is that deceleration. Or you could just say the acceleration is, and then give me a negative number, but don't say it yet. Look at the velocity graph. Yeah.
If you say the deceleration is, do you still have to give a negative number, or do you give a positive number if you say deceleration?
I'd give a positive number. Yeah. Or you could say the acceleration is such and such backward, or give a direction. Like if you're throwing a ball up in the air on its way up, the ball is going to slow down. So you could say the acceleration of the ball is 10 meters per second squared downward. You could also say the acceleration of the ball is negative 10 meters per second squared because it's going up, but it's accelerating the other way. Yeah.
You want me to answer how fast it's going?
Sure. Go ahead and answer. What's the acceleration of that?
Well, since it's going, since it's in like tens and it's going down 1 over 2, that's like half of 10, so 5 or 5.
Yeah, and it's kind of unfortunate that I don't have 5 meter per second increments on here, but so at 0 seconds it's going 50, at 1 second it's going 45, at 2 seconds it's going 40, and at 3 seconds it's going 35. So think about what's happening to the velocity during a second. It's losing 5 meters per second. And what's the graph on the right going to look like when we look at it? Straight line, up, down, flat, horizontal, and it should be on -5. So there's the acceleration. Now, this last case, just look at this one for now. This is a distance versus time. Suppose somebody made that with a motion sensor. What kind of acceleration is that?
It's a constant.
Constant acceleration?
No, 0, but like constant speed.
Yeah, if you wanted to make this graph, you would stand next to the sensor, and you wouldn't walk away speeding up or slowing down. This is walking away from the sensor slowing down. This is walking away from the sensor speeding up. You're covering more distance as you go. Here you're covering less distance as you go. Here, it's the same distance is covered every second. I should have even, oh, I did. Ooh, good. So looking at that, what is the velocity? How many meters is somebody moving in 1 second? 1. So this would be the 1 second mark, and they would be right at the 1 meter mark. 2 second mark, they're at the 2 meter mark. So this is somebody going 1 meter per second. The velocity graph is just flat right across 1 meter per second. Now what's the acceleration graph going to look like? 0. It's constant, no acceleration. So hopefully by looking at those, you see the connection between the three. We're not really going to do anything with that right now, but in the future you'll have to interpret graphs and figure some more stuff out from graphs. Hope that sets the stage. But one thing I do want you to write on this before we move on to the bottom is all 3 graphs represent the same event. So I just want you to make note that these 3 graphs go together. They're the same person doing the same thing, or the same car doing the same thing. Those 3 graphs are the same thing. They're just 3 different ways to represent it with either distance, velocity, or acceleration. Now, down to the bottom, this is, after this we'll watch the penny drop and you can relax for a little while. The penny drop, I think they'll talk about this. Maybe they won't, but I think they will. On Earth, do you remember what I said the acceleration of gravity was? How many meters per second do you speed up every second if you fall? 32 feet per second.
96 meters.
It's got a 9 in it. 9.8 meters per second squared. That's your acceleration on Earth, that there's no air affecting you and you're just falling in free fall with only gravity pulling on you. Now when you've got air pushing on you, it might not be quite that fast. And that number is conveniently close to 10. So a lot of times, unless I specify, make sure you use the precise real value. We're just going to be using 10 meters per second squared, because it makes the math really easy and we can talk about things quickly. So this means if something falls from a height, for every second that it falls, 10 meters per second is added to its velocity. And so if you fall for 1 second, you're going 10, 2 seconds, you're going 20, 3 seconds. That graph at the top of the page, those 3 graphs, those are representative of somebody in free fall.